Hello, guys. My name is Alex Hidalgo. I'm a technical consulting engineer in the VPN team, Max VPN team. And today we'll talk about encryption, integrity, and HMAC errors. This is the agenda for today. We'll talk about the need for encryption. We'll go over the concepts of encryption and integrity. We'll give you some examples for the best practices for both encryption and integrity, and at the end we will talk about a little bit about HMAC errors and some troubleshooting tips. After that, we will have a Q&A session in case you need any further information. So let's start. The major problems for network administrators are the following. Packet snooping refers to when intruders capture and decode traffic, this with the purpose of obtaining usernames and passwords, also sensitive data. Theft of data refers to almost the same packet snooping, but this has the purpose to use this information with a different purpose than intended, or also to get the benefit out of that, to sell that information or to use it to obtain a different result. Also, impersonation. This refers to when an intruder assumes the role of a legitimate device, but in this case, well, it is not legitimate. The intruder efficiently assumes the role of an authorized user. In this case, if we see this diagram right here, the sniffer is placed in here between the firewall and the internet, and also this sniffer can be put in between a user and the internal network, or between users right here. So this leads us to the next concept, which is the man-in-the-middle attack. This is a general term for when a perpetrator positions himself in a conversation between a user and application, or between users. This with the purpose to either eavesdrop or to impersonate one of the parties, making it appear as if a normal exchange of information is underway. The goal for this attack is to steal personal information, such as login credentials, account details, and credit card numbers. Just to put in like a different example, man-in-the-middle attack is the equivalent of a mailman opening up your bank statement, writing down your account details or account information, then resealing the envelope and delivering it to your door. Encryption. We'll talk about now encryption. Encryption is a process in which plain data is converted into ciphered data. This ciphered data this plain data is ciphered using different methodologies depending on the encryption algorithm that we use, and this ensures data privacy, integrity, and also provides authentication. In the next slide, we will see how encryption works. This is the methodology of how we can convert plain text data into ciphered data. So in here, in this example, we will send 1 to 3 across this network, and this data is modified according to a key. This key is a sequence of digits that decrypts and encrypts the message. Each device on each end of the network has 3 different keys. The first one is the private key that is used to sign messages. This is kept a secret and is never shared. So the source does not know the private key of the destination, and the destination does not know the private key of the source. Also, they have a public key. This one is shared, and it's used by others to verify the signature. And well, we also have a secret shared key, and this is used to encrypt data using a symmetric encryption algorithm. And yeah, in this case, we will send first the plain data. In this example, 1 to 3. This is encrypted and only readable if decrypted by the correct key. So with the correct pre-shared key, then data is encrypted using a mathematical formula to scramble data, and upon reception on the other side, the same pre-shared key is used to decrypt this data, and well, we now get the clear text data again. This will prevent a man in the middle attack, because if a sniffer positions himself in any of these endpoints and gets the information that we are sending, they won't be able to know what this packet contains. So now we will see an example. In this case, we will compare unencrypted and encrypted packets. In this example, I'm using HTTP. As you can see here, this is a test site using HTTP. And you can know that this site is not secure because it has a crossed lock in here. And well, you can see the information that this page contains. So it's just an example page. So yeah, in here we also configured set up a Wireshark capture. In this case, I used my own machine to run this packet capture, but this might as well be an attacker sniffing packets on my router or my switch. And well, you can see here that when we create the connection to this non-secure site, we see on the packet, if we open that packet up, we can see the HTML code for this site. So in case that we were trying to log in or use credentials or make a payment, if someone intercepted this packet, they will be able to know the information that we are exchanging between the endpoint and the non-secure server. But now let's see an example with HTTPS. In this case, the S stands for secure, and well, in this case, HTTP uses SSL as an encryption method. And again, I used a different test site. In this case, it is using HTTPS, and we can know that this site is secure because the browser shows now the lock without the cross in it, so we know it's secure. And well, the IP of this FKDN is 104.154.89.105. HTTPS uses port 443, but in this example, this test page is using port 1012. And again, I run the same Wireshark capture in here, and well, we can know here that it is secure because it is using TLS, transport layer socket, and then we can see here, if we open up these packets, we can see that instead of seeing the HTML information or any username or password, we only see encrypted application data. In this case, if we intercepted this packet, we won't be able to know what is exchanged between these two servers, between the machine and the secure server. So now let's talk about data integrity. This refers to the maintenance and assurance of data accuracy over its entire life cycle. So when sensitive information is exchanged, the receiver must have the assurance that the message has come intact from the intended sender, and that is not modified. in transit. So in this example, we have the word fox. We use a hash function to get a fixed length string. And you can see here that if we modify the input and if we modify the input of the hash function, for example, in here, the red fox runs across the ice. If we hash this input, then we will see a different, a completely different output. And also, if we modify instead of runs, if we said that the red fox walks across the ice, then we will again see a completely different output. So this is how we can know that we are using a good hashing algorithm, because it displays an avalanche effect. So this means that even a single bit of a character, if a single bit of a character is changed, the result of the hash will be completely different. Another example is here. For example, if we use Cisco with a capital C, this is the MD hash that we get. It starts with the 7 and ends with the 5. But if we use the input Cisco, but with a lowercase c, we can see that this is completely different than the first one. So this one starts with the D and also ends with the D. And the same thing here with the SHA-1 hash. This one starts with A and ends with 8. And the other one with the lowercase c starts with the 7 and ends with the 5. We get different lengths because we are using different hashing parameters here. And this is how we can verify that the information that we are sending across the network has not been tampered with. Because here, what we do when we send any information over the network using integrity checks is that if we try to send a message M, we will hash this function using the same, well, the hash function, we should be using the same on both sides. If we use this, if we hash this message M, we will get a value H1. When we send this message across the network, we will send the message M along with the hash value H1. And when it's received on the destination, the same message M is hashed using the same function as the sender is using. And well, we will get the value H2. Then when we get the hash from the message that we receive, we will compare H1 and H2. And if these are the same, then we know that the message has not been tampered with, and we accept this packet. In case that that we don't pass the integrity check, then this packet is dropped. Now, these are some examples for best practices for integrity. Oh, sorry, for encryption, we need to avoid DES and 3DS. These are now considered deprecating, and we should avoid using those. And also for integrity, we need to avoid using MD5 and SHA-1. Instead of these encryption and integrity algorithms, the acceptable ones for encryption will be AES-256, but this can also be AES-192, AES-128, and so on. And for integrity, we will need to use SHA-256, SHA-384, and SHA-512. These integrity algorithms belong to the next generation encryption. So whenever possible, we need to prefer using next generation encryption. Now, what happens when a packet does not pass its integrity check? Then on Cisco devices, specifically on routers, we will see this HMAC error. In this case, it says that IPsec SA is receiving an HMAC error. The HMAC errors are the result of packets being dropped due to corruption. In this case, it does not necessarily mean that an attacker tampered with the packet, but usually what happens is that the ISP could be messing in some way with the packet, altering its contents, and that packet sometimes gets corrupted. So in this case, when we see this error, the packet is not passing their hash algorithm check, and therefore, their payload has been tampered with. And instead of allowing the packet to go in, this device drops these packets. An example in SD1 in the SD1 world, when we have 2B edges, in order to create a BFD session, we need an IPsec tunnel. So if we are seeing HMAC errors over the IPsec tunnel, obviously these packets will be dropped. It does not necessarily mean that the tunnel is down, but obviously if we are seeing HMAC errors and the packets going across the tunnel will be affected. So in case that a BFD session over an IPsec tunnel does not come up due to HMAC errors, it usually means that the packets have been tampered with, and the most likely could be the ISP messing with the packets. Also, this happens when we run routing protocols across the tunnel. Sometimes, if we receive these HMAC errors, the BGP sessions or routing sessions won't come up because traffic going across the tunnel will be affected. But as mentioned before, this does not necessarily mean that that the IPsec tunnel is down. So in this case, if we receive these errors, it means that the packet is dropped due to integrity check error. So here are the references in case you need to dig deeper into the concept that we went over this session. So now I would like to ask you if you have any question. If something was not clear, you can just let me know now.
I've asked them on the Q&A if you got them there.
Sorry, Mark, can you repeat that?
We have a question from Mark on Q&A, Alex, and it's what level of various assurance has our encryption implementation gone through?
Sorry, can you repeat that again, please?
So what level of assurance of the encryption implementation go through? There's FIPS, common criteria, any others more recently, or I'm just wondering how far we've taken that, because that's usually the first thing that a lot of customers will ask for in particular sectors. Sure.
Yeah, we have in this link here. We should always prefer next generation cryptography, so that covers encryption and integrity algorithms. If you want, this session, this presentation will be sent to all of you, and you can check this link, and it contains the best practices with all of the parameters to avoid and parameters to prefer. On my best practices slide, I put in just a few examples of the well-known parameters used usually by customers. But in here, you can see in case a customer uses something something not supported, you can also see the next available encryption or integrity algorithm to use. Okay, Mark, does that answer your question, or do you have?
Slightly different question, but that's okay. I mean, the one I was asking for was third-party assurances. So, you know, third-party assurance regimes such as FIPS, you know, common criteria, EL, any others that have gone through validation of the way we've implemented encryption rather than the encryption algorithms themselves, which is obviously part of it, but because that's one that typically comes up. I'm just wondering if that's been expanded out into other third-party assurance programs.
Oh, well, in this case, if we are sending traffic over a network, then and specifically over a VPN, then with these encryption algorithms, we can be sure that that even if the ISP is trying to go over what you're sending over the network, if you are using strong encryption algorithms, then they shouldn't be able to crack your messages, if that's what you're referring to, Mark.
Thanks.
Alex, one quick question. This is Zahir. In terms of the interoperability between different hashing algorithms and also encryption types, what is our story around that, and how do we track, you know, which ones are supported to interop with each other?
Oh, yeah. So ideally, when you create a VPN or an IPsec session, a NIC session, you should always be using the same parameters between both endpoints. So, for example, if you are creating a side-to-side tunnel or an IPsec session between two devices, they should agree on one parameter. So, for example, you create an IPv2 policy where you set up the encryption and hashing algorithms to use, and you should use the same algorithms on both sides. So if you are using, for example, SHA-1 on one side and MD5 on the other side, then the IPsec session or IX session won't be able to come up, because they need to agree on one parameter to use, and well, one encryption algorithm or one SHA algorithm to use. Because if we go back to this diagram right here, in this case, well, actually, this one shows it better. So in case we are using here, for example, SHA-1 on this side to generate the hash value H1, and if we use MD5 on this one, then obviously the hashing values won't be the same. So that's one of the checks that the IPsec sessions runs through before actually reaching to this point. They should agree on one parameter before even before the IPsec session comes up. So to answer your question, they should use the same parameters to build an encrypted session.
Okay, thank you.
Yeah. Okay, guys. Any other questions? Okay. In case there are no questions for now, we will send this presentation to all of you. And in case you're reviewing the presentations later, in case you have any other questions, you can reach me over Teams, or you can also reach any of the VPN engineers, and we will be glad to help you in case you have any further questions or need additional information. So for now, well, I would like to thank you all very much for joining the meeting. And well, I hope you have a great rest of your day. Thank you very much again.
Thank you so much, Alex, and thank you so much, team, for joining. Have a nice day.
Thank you.